Hey people, welcome back to the first lesson here. Worked example, theory of elastic bending. There's the first problem. Is to determine the maximum bending stress that will occur in a timber beam of rectangular section. There's the dimensions when the bending moment of that is applied about the x-axis. Right, as I said before, state the formula, see what's given, see what's needed. Okay, and if you've got a formula and you've got all the variables except one, make the unknown the subject of the formula, put the values in, and get the answer. Okay, so that's what you basically do in this section here. So let's see. I'm going to state the formula. Right, so let's see. M over I is equal to F over Y. You know, people over the years, a lot of students ask me and say, "Sir, do you remember all the formula?" I didn't wake up one morning and decide that I'm going to remember all the formula for structures. No, I didn't do that. I write it down every time, and also I give you a mark for it, okay, a mark or two. And every time you write it down, it stays in your brain just a little bit longer, okay? So write it down so you can see what's needed, see what's required, right? Let's see. Determine, so we need to find F. The question is, we need to find F. That's the question. And that is D over there, and that's B there, and that is M over there. Okay, right, so let me draw it out. The beam determined, let me draw that quickly there. There's my x-axis, and there's my y-axis. Right, let me just take it off. That's x-x. Oh, sorry. BB, naughty me. Y. And of course, where the two axes meet each other, that's the position of its centroid, as we know. Okay. And B is the narrow side, so B is equal. I'll change that over there. B is equal to 50 millimeters, and D is the vertical longest side, is equal to 150 millimeters. Right, so let's see. We know this. Do we know this? Yes, this is equal to D over 2, which is 75 millimeters. Do we know this? We don't know it, but we can work it out. Okay, so what's the second moment of area for the rectangle? Yippee, we know it. It's BD cubed over 12. So you can either work it out individually and plug it into the formula at the end, which I will do now. So I'm going to say I is equal to BD cubed over 12. And B is 50 times 150 cubed. 150 cubed over 12. And what answer do I get there? Do the calculation and check me against you. Okay, so let's see there. And I got 14062. 14062 500. And what's the units of measurement? Yes, you know, I'm glad you remember. It's millimeters to the fourth. Okay, not centimeters, not millimeters cubed, not millimeters squared, millimeters to the fourth. Okay, so let's see. So therefore, from that, F is equal to M times Y over I. Okay, and M, now notice, that's millimeters to the fourth, and that's given in Newton meters. Be careful. We need to convert 600 Newton meters to 600 Newton millimeters. How do we do that? We're not converting the newtons. We're converting the meters to the millimeters. We multiply by 1,000. So the moment there is 600,000, or you can say times 10 to the power 3, if you're feeling really smart exponentially, times Y. What's Y? Y is the distance from the centroid to the furthermost fibers. It's D over 2, which is 75. Divided by I, that big number we just found over there, 14062 500. And you stop the video and you do the calculation and you check that you get the same answer as me. And yes, you should have gotten 3.20, 3.20, and it's a stress. It will be in, what's the formula for stress? Stress is force over area, so it will be newtons per millimeter squared. Okay, there we go. Here we go. Okay, so determine the maximum stress that will occur in the timber beam of there's a section at that moment there about its x-axis, and of course if I drew a side view of that there, the beam is sitting like this, and there's its supports roughly, and of course there's the x-axis or the neutral axis running over there, and that height there is the 150 millimeter height. Okay, and there's the load sitting over there. So the stresses in the fibers in tension and bending, the furthermost fibers from top and bottom, will be 3.20 newtons per millimeter squared. Okay, so people, that is how we did the first example there, using the theory of elastic bending formula to work at the stresses in the fibers. Okay, and I will quickly clean the board and do example number 2. Alright people, this problem number 2. A timber beam of rectangular section 240 by 80 is simply supported over a span of 4 meters if the permissible bending stress, another word for permissible is allowable, or another word is maximum, okay, is 5 newtons per millimeter squared. Determine the maximum allowable UDL, okay, that the beam may carry applied perpendicular to the x-axis. That means when it's put normally, when it's placed normally with that side vertical, okay, and that side horizontal. That's B, that's D. And then B applied to the perpendicular to the y-axis. That means in the second case, where the beam is turned to 90 degrees, where that is now placed horizontally and that's placed vertically. Okay, just think about for a moment, which one, okay, if we place the beam this way, okay, I'll just draw it in quickly. Come on. Okay, that's 80 mils there, and that's 240 mils there. Okay, B is that, and D is that. Okay, now if we place the beam like this, okay, in number A, and we load it up, and then we turn the beam to 90 degrees, where that is now sitting horizontally and that's vertical, okay, and we load it up again, which way do we think the beam will carry the load best? A or B? Think about it. Okay, let's prove what it's going to do. Right, let's see. A timber beam, let's see what we got, let's see what we need. That is D. I want it. That is D. That is B. And that's F, giving us F. And they want us to determine small w. Okay, so let's draw out the pictures. Timber beam of that is supported over a span and there's my, okay, there's my UDL, which I don't know, okay, and the span is big L, is equal to 4 meters, and to determine the max, that there is the question. Okay, so a timber beam of rectangular section, there's the dimensions over there as I gave to you. Okay, there's the dimensions. Okay, and of course there's the y-axis and there's the x-axis as always. y-x-x, there's its centroid. Okay, so say the beam is placed this way, it says with F being that, determine the maximum allowable UDL. Right, so let's see. State the formula, see what you got, see what you need. Right, M over I is equal to F over Y. Okay, so let's see. Right, people, so let's see. Can we work M out? No, we can't because we don't have a UDL. That's given. Okay, that's given there. Do we know what Y is? Yes, for number A, with the beam placed this way, that means the load is the beam is placed this way and is carrying load vertically. That means at right angle to the x axis. So y in case number A will be equal to 240 over 2. So we know that. Can we work at I? Yes, let's do that. We can work at I. What's the formula for I? I is BD cubed over 12. So I'm going to say number A, IXX is equal to BD cubed over 12. What am I doing? BD cubed over 12. And it is 18 times 240 cubed over 12. And it is equal to, check your answers against mine. I get 92160, 92160 millimeters to the fourth. Okay, so that's IXX. Okay, I'm somehow going to work at IYY as well. IYY, let me squeeze in here. IYY is equal to BD cubed over 12. Okay, what's B, what's D? B is the side parallel to the axis you're taking moments about. So B is now 240. B is 240 and D is now 80 cubed over 12. Okay, and check your answer against mine. I get that to be 10 to 40 naught millimeters to the fourth. Okay, so I've worked at IXX for number A and I've worked at IYY for number B. Right, the question there says determine the maximum allowable UDL that the beam may carry applied to the perpendicular x-axis. Right, so let's see. So we know we have a similarly supported beam at its ends, span is 4 meters, and the UDL is along the whole length. We need to find W. Now, in this folder on Blackboard, I've got a PDF called beam formula. Okay, I place it in the simply supported beams folder as well. Now, because this beam is simply supported at its ends, it's got the UDL along its whole length. We call this here, we call it a standard case. Okay, now a standard case means that there's lots of symmetry involved. Okay, so from here I'll be able to work out the reactions. I can draw the shear force diagram, I can draw the bending moment diagram. Okay, but because it's a standard case, it means I can just go to the formula and just pick out a formula, put in the values given, and get the answer as easy as that. Right, I'm going to go to my beam formula and I'm going to go down my tables there and I'm going to find my beam that looks like the one that we got. I'm going down, I'm going down, I'm going down, I'm going down, there we go. Yes, there's my beam. I'm going to zoom in slightly. Okay, there's my beam there. Okay, there's my beam. It's simply supported at both ends. It's got a UDL. Notice here UDL is represented by W, which is the same as small w times L. Yeah, the total load given by the UDL is the UDL multiplied by small l. The span here for this small l, as is just big L. So notice that the reaction at A is equal to the reaction B. It is equal to W over 2. And then very importantly there, that's what we want. Bending moment. Okay. The maximum bending moment for that beam will be at the center and it's equal to WL over 8, where W is equal to WL. So if I put this into there, I'm going to get WL squared over 8. Okay, you need to remember the formula, and that is the formula for the maximum bending moment at the center of a similarly supported beam with a UDL along its whole length. Okay, WL squared over 8. Right, so we know, let me change the color here. We know that the moment at the center of the beam is equal to WL squared over 8. Okay, but from here we also know, if I make M the subject of the formula here, M is equal to IF over Y. Okay, so if M is equal to that, and M is also equal to that. Therefore, we can say that all of this is equal to all of that. So therefore, I can say W L squared over 8 is equal to I F over Y. Okay, so let's look at this formula here. Do I know L? L is equal to 4,000 millimeters. Do I know I? Yes. For number A, IXX, I got it, so I know that over there. And F is given. Okay, F is given. And Y is D over 2. So that means I know all the variables. If I make W the subject of the formula there, I can work at W for number A and work at W for number B, and it's job done. And have you thought about which one should be bigger, which one should be smaller? Because the beam is stronger placed with the longer side vertical, we expect a bigger answer by number A and a smaller answer by number B. Okay, so I'm going to clean the board quickly, and then we're going to measure the answer and compare the two with each other. Right, people, I've taken this formula here. Okay, WL squared over 8 is equal to IF over Y. I've written it over there. So for number A, I got that's equal to 8 times, and because number A, the beam is placed vertically, it will be IXX times F, which we know, over Y. And what's Y? Y is D over 2. It will be D over 2. I write it like that, for example, times L squared. And let's put the values in. So it's 8 times. And what's IXX? IXX was 92.16. 0.0 millimeters to the fourth. What's F? F is 5 newtons per millimeter squared over Y. Now remember, the beam is placed like this. Y is equal to D over 2. It's 120 times L. L is 4, but it is 4,000 squared. If you write it as 4, it will be meters. All the others will be millimeters, and the answer will be wrong. You will get a massively big answer. Right? Is equal to, check my answer, you should get 1.92, and it's a UDL, so it's going to be newtons per millimeter. Okay, so the UDL for number A, given all these factors here, is equal to 1.92 newtons per millimeter. Okay, right, number B, it says there, work out the UDL that the beam can carry perpendicular to the y-y axis. That means taking all these factors into account, but the beam is now turned to 90 degrees, so that the 80 millimeter is now lying vertical and the 240 horizontal. Right, I'm going to clean the board quickly, we do the calculation and see what we get. Oops, this should be number B. Here we go. Okay, number B. Alright, there we go. So the formula is the same. B is equal to small w equal to 8IYY this time. Y, because the beam is turned to 90 degrees and bending is about the y axis. F is the same and Y is now 80 over 2. Okay, and L is the same. So let's see. So it's 8 times IYY. And what did we get for IYY? It was 10,240. 10,240, 000 times F. F is still 5. Bending in the 5 is remain the same. Divided by Y. Y is D over 2. But D is now equal to 80. So it's 40. Okay. Times 4,000 squared. Not 4,000 millimeters squared. Okay. Work at the answer. Check my answer. And you should get 0.64, and it's a UDL. It's newtons per millimeter. Okay, well, what happened there? Okay, so people there, if we check answer A, the answer we got there was 1.92 newtons per millimeter, and the answer by number B we got 0.64 millimeters. Can you see? We just proved that when the beam is sitting this way, it can actually take a bigger punch. It can carry more load than if it's placed, can I say flat? If it's placed like that. 80 over there and 240 over there. Okay, that is why whenever we place a beam, we always place it so-called vertically. We place with the deeper side vertically so it can carry more load that way as opposed to carry load that way. Okay, so people, there's number 2 done, and I will see you in the next lesson for lesson number 3.